Alrighty, howdy folks. I have a feeling this is going to be pretty much the last uh, lecture. I'm going to cover 7.5 and also 6.1. 6.1 you will find to be fairly straightforward, and this particular section is even more straightforward. Alright, this is about applications in the sense. If you have been wondering, hey, why are we doing this stupid Laplace transforms in a differential equations class? Well, today is the answer to that question. We can solve differential equations using Laplace transforms. That's the whole idea. How to go about doing that is precisely what we are going to cover today. Let's say the problem statement looks something like this. Solve the differential equation dy dt plus 2y equals t with an initial condition y of 0 equals -1, and you need to use Laplace transform for it. So how do we do this? The first thing is to take the Laplace transform of both sides of the differential equation. The derivative y, right, dy dt, what's the Laplace of that? In the previous section, we talked about Laplace of f prime of t being s times uppercase f of s minus y of 0, minus f of 0 rather. So Laplace of dy dt in a similar way turns out to be s times uppercase y of s minus lowercase y of 0. Okay, that takes care of the Laplace of dy dt. Plus 2 times the Laplace of y is uppercase y of s. You must have a way of distinguishing your lowercase y's from the uppercase y's. If you don't, you are going to be in some serious trouble. So do whatever you want. I particularly like to put serifs on my y's and write the y like that. And I think my lowercase y, I just write like that, and uppercase y with serifs on it. That seems to work for me. Okay, all right. So here, what's the next step? Let's plug in the value of y of 0 to be -1 in the next step. And let's solve for y of s. There are two terms that have a y of s in it. Excuse me. And let's factor that s plus, factor that y of s, and we get this, right? And so we basically solve for y of s. Wait, what has this got to do with solving the differential equation? So let me pose that as a question before answering it. What are we supposed to do when we are given a differential equation and somebody says solve it? Would you agree we need to find y, lowercase y? To be more precise, lowercase y of t in this case. Are we anywhere close to finding a lowercase y of t? What did we find here? Uppercase y of s. What's the relationship between lowercase y of t and uppercase y of s? Y of s is the Laplace of y of t. So if you know y of s, can you find y of t? Yeah. Find the Laplace inverse. That's it. Okay. Now, when it comes to finding the Laplace inverse of this, I have already taught you everything, right? You know exactly how to find the Laplace inverse of something like this. So I'm not going to go in detail. In this case, I just split it into partial fractions, and the Laplace inverse of 1 over s square is just t, and 1 over s is 1, 1 over s plus 2 is e to the -2t, and so on. So that's what I did. Of course, I simplified the 1/4 1 times 1 over s plus 2 minus this to -3/4. And that's it, right? So as you can see, the concept is very straightforward. Given a differential equation, you take the Laplace in Laplace transform on both sides, solve for y of s, and invert it. Another example, second order differential equation. Y double prime, the Laplace is s square uppercase y of s minus s y of 0 minus y prime of 0. Okay, and so this is what you see is the Laplace of y double prime of 0 minus 4 times Laplace of y prime is these two terms plus 4 times Laplace of y is uppercase y, t cubed, the Laplace is 6 over s to the 4. Next, plug in the values of y of 0 and y prime of 0 into this and solve for y of s. Once you get y of s, invert it and partial fraction decomposition and invert it after that. That's it. What did I do? Oh. What? Yeah. Just invert this. So I'm not going to ask you anything beyond second order differential equation. These are the problems that I'm going to ask you. Simple, straightforward kind of problems like this. Cool. Guess what? We're done with 7.5. Let's move on to 6.1. This is what is called Cauchy Euler equation. It is not Cauchy, it is not Euler, it is Cauchy Euler equation. So let's look at how to solve Cauchy Euler equations. First of all, what in the world is the form of an nth order Cauchy Euler equation? This is the form. Take a good look at it. Let's focus on just the first term. A sub n x to the n d to the ny dx to the n. You remember in chapter 4, we had constant coefficients. That means our equation looked like a sub n d to the ny dx to the n. But now we have this a sub n times x to the n. And the next term, a sub n minus 1, which is the coefficient of d to the n minus 1 y dx to the n minus 1, is multiplied by x to the n minus 1. So that's got to be the form. Nth derivative multiplied by x to the n and a to the n minus 1th derivative multiplied by x to the n minus 1 and a constant a sub n minus 1, and so on. So a sub 1 x dy dx plus a sub 0 y is equal to g of x. Quick question. Is this linear? Is every derivative raised to a power of 1, including the 0th derivative? Yep. Is every coefficient of the derivative purely a function of x? Yep. This a sub n x to the n is a function of x. A sub n minus 1 x to the n minus 1 is also a function of x. So everything is a function of x. All the coefficients are functions of x. And the right hand side is just a pure function of x. So this is linear. Cool. And how do you solve a Cauchy Euler equation? I want to help you understand. I want to do this. I want to contrast this with the constant coefficient stuff that you are very, very familiar with by now. Okay. Let's focus only on second order Cauchy Euler equations. Is this ay double prime plus by prime plus cy equal to 0? Isn't that the form of a homogeneous constant coefficient second order equation? Right? What is a second order Cauchy Euler equation? What would it look like? You have ax square y double prime plus bx y prime plus cy equal to 0. Do you by any chance remember how we proceeded to solve this equation? We said assume y equals Do you remember what we assumed? Y equals in the constant coefficient case. Y equals e to the mx, right? Now what do we assume here? You assume y equals x to the m to be a solution. Okay. Why? I'll show it. I'll show you why you need to assume possibly x to the m could be a good solution. How people found that out, I'll show you in just a bit. And then what do? Well, you plug and figure out y prime, y double prime, plug into the equation, and same thing you do here as well, right? And when you do, you can factor out e to the mx. Here you can factor out x to the m. E to the mx cannot be 0. X to the m cannot be 0, right? Unless x is equal to 0. We cannot let x equal to 0 because that would cause all of this to just, all these derivative terms will go to 0. So x equals 0 is never in the domain of this one. So we need not worry about that part. And what does that give us? It gives us this characteristic equation am square plus bm plus c equal to 0. Here we get a similar characteristic equation. Am square plus b minus a times m. I grouped this m. We have am square minus am plus bm. That's what I wrote here as that minus am plus bm as b minus a, the quantity, times m. So we get a characteristic equation even in this case, just like in the previous one. And we know what to do. That is, we need to solve for m. We need to find the roots of this characteristic equation. Let's say 2 and 3 are the roots. Do we know what the solutions, two solutions are? Yep, x square and x cube, right? M, we are saying, has two values, 2 and 3. So there must be two solutions, x square and x cube. The only question is, are they linearly independent? Yeah, x square and x cube are linearly independent, so we are done. So that would be the idea. Okay. Now let me answer that question. How did someone know how to assume y equals x to the m to be a solution? Simple. Somebody said, hey, what if we were to have a first order equation? For this, we know exactly how to proceed. You can do separation of variables and solve. And for that, turns out to be x to the negative b over a is the solution, or x to some kind of a m. That's the idea. Okay. All right. Now, again, we will have three cases: discriminant greater than 0, equal to 0, less than 0. Greater than 0, then roots are real and unequal, just like 2 and 3 that I said, right? So in that case, x to the m1 and x to the m2 would be the two solutions. And because m1 is not equal to m2, we said real and unequal, so m1 is not equal to m2, so they are guaranteed to be linearly independent. Okay, and so the general solution is a constant c1 times x to the m1 plus constant c2 times the second solution x to the m2. Simple. Now, case 2, when the discriminant is equal to 0, that is, the two roots are equal. They are real but equal. And in that case, we cannot say we have two solutions. This x to the negative b minus a over 2a, x to m, that is one solution. Now, how do we find a second solution? Go back to 4.3. 4.2. 4.2 is where we knew the differential equation, we knew one solution, and we found the second solution. That big integral e to the negative integral of p of x dx over y1 square dx, that stuff, that's what we can do. So you don't have to do this every single time. I'll just show you what happens in this case. if you were to have a generic ax square y double prime and it turns out that the two roots are the same, that means we know one solution, and I figured out p of x, negative integral of p of x, and all of this. So e raised to natural log, e raised to negative, this whole thing just becomes natural log of x. So this is our so-called u of x. y2 is equal to y1 times u of x. You know what that means? The second solution is x to the m times natural log of x. Back in constant coefficient case, if two solutions are equal, we said e to the m1x and x e to the mx. E to the mx and x e to the mx were the two solutions we said. Here we multiply by natural log of x, whereas in the previous case we had multiplied by x. Okay. Now, if there were to be a third order, then you would have to multiply by the quantity natural log of x squared. This natural log of x, you must multiply by the square of that one. So y2 is nothing but natural log of x times y1. Okay, cool. Oh, by the way, maybe I should have been careful. This is basically natural log of x, that quantity times y1. I'm not saying natural log of x times y1. Okay, when the discriminant is equal to 0, just trying to summarize what we got, x to the m would be one solution and x to the m natural log of x to the m times natural log of x would be the second solution, and the general solution is a linear combination of the two. Cool. Final case. What if the discriminant is less than 0? That means the roots are alpha plus or minus I beta. They are complex conjugates, and so we should say x to the alpha plus I beta and x to the alpha minus I beta are the two solutions. They are linearly independent. But when it comes to finding the general solution, we can say some d1 x to the alpha plus I beta plus d2 x to the alpha minus I beta. However, there is a nice way of, you got to be a little clever about this, just like we were in the constant coefficients case. We can use the Euler relationship. E to the I theta is equal to cosine theta plus I sine theta. Right? And for that, we can write x to the I beta as e raised to natural log of x to the I beta. That's the trick we'll do. A simple x to the I beta, we will write that as e to the natural log of x to the I beta. When we do that, on the exponent, we can bring this I beta to the front. So e to the I beta times natural log of x. Now this is looking like e to the I theta to me, with theta being beta times natural log of x. Let me repeat that. This looks like e to the I theta, where theta is beta natural log of x. But I already said e to the I theta, Euler said, is cosine theta, so cosine of beta natural log of x, plus I sine theta. Cool. And similarly, x to the negative I beta would be cosine of beta natural log of x minus I sine beta natural log of x. So I'm going to replace the x to the I beta and x to the negative I beta with the Euler relationships, collect all the terms, and this whole thing, ladies and gentlemen, simplifies to x to the alpha times c1 cosine beta natural log of x plus c2 sine beta natural log of x. Cool? All right. I'm going to summarize the whole thing in the next slide. So, when you have a Cauchy-Euler equation of this kind, This is the characteristic equation. Okay, am square plus b minus a times m plus c equal to 0. And you can solve this in any way you want. You don't need to use this quadratic formula. Find the roots. If the roots are real and unequal, x to the m1 and x to the m2 are the two solutions, and the general solution is this. On the other hand, if m1 equals m2, then the fundamental set of solutions would be x to the m and x to the m natural log of x, and the general solution would be a linear combination of them. Complex conjugates, then general solution is this. Cool. And I'm going to show you 3 problems and we're done. Would you agree a equals 1, b equals -4, and c equals 6? Do you remember the form of the characteristic equation? am square plus b minus a times m plus c is equal to 0. So I apply that. I plug in the numbers a, b, c and get the quadratic equation. M minus 2 times m minus 3. So the roots are m equals 2 and m equals 3. So the two solutions are x square and x cube, and the general solution is c1x square plus c2x cube. Done. Done. Next, a equals 1, b equals -5, c equals 9. Am square plus b minus a times m plus c will give us this equation. M minus 3 the quantity square. So m equals 3 or m equals 3. Real and equal solutions. Discriminant happens to be 25 minus, this one. 36 minus 4 times 9 is 36. Discriminant is 0. So no wonder the roots came out to be equal. So what did we say? c1 x cube plus c2 x cube natural log of x multiplied by a natural log of x. That's your solution. Finally, can you see what I'm doing here? The first one I made sure it came out as real and unequal. Second one, real and equal. Can you take a wild guess what this would be? Yep, you guys are smart. Complex conjugates. A equals 1, blah, 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 plug. Aha. Roots. Turns out to be 3 plus or minus I. Alpha is 3, beta is what? 1. Yep. Alpha 3, so x to the alpha, x cube, times c1 cosine beta natural log of x. So c1 cosine natural log of x plus c2 sine natural log of x. Ladies and gentlemen, that's it. We are done with this course. I want to say thank you. You guys have been good. I wish you all really the best in your lives. May all your dreams come true. May you live a long, fruitful, peaceful, and a productive life. Thank you, guys.